Okay, in this example, we have the same reaction with that carbon monoxide and the hydrogen to produce methanol. We are taking 15 grams of carbon monoxide and placing it into a container with 5.1 grams of hydrogen. And they would like us to solve for the limiting reactant. So we're going to go about this the same way as before. Okay, we're going to put down our BCA table, but you'll notice in a BCA table, because we're using coefficients as a mole ratio, we are only allowed to put in mole values into a BCA table. Our question doesn't give us mole values of the carbon monoxide or the hydrogen. So your first step is to convert those given grams into moles. So that before I do BCA, I have to have moles of our givens. So we're going to take 15 grams of carbon monoxide and we're going to convert that into moles. Looking at the periodic table, we're going to calculate the molar mass of carbon monoxide. Carbon is 12.01 and oxygen is 16. So there's a molar mass of 28.01 per mole, grams per mole of carbon monoxide. Those grams cancel and you're left with moles of CO. Okay, so 15 divided by 28.01. And I get this really long number in the calculator. 4 decimal places is sufficient for us. So this is 0.5355 moles of carbon monoxide. And remember that we are still working with our before value. We're going to repeat this process for the hydrogen. Hydrogen starts with 5.1 grams. You have 2 hydrogens, so its molar mass is 2.02 grams. Grams hydrogen cancel, and you solve for moles of hydrogen. So 5.1 divided by 2.02, and we get 2.5248 moles of H2 as our before value. Now that I have moles of each reactant, now I can do BCA. Okay? It would be incorrect for me to put the grams into the BCA chart. I have to put in moles. So we're going to construct our BCA table. You always start with that reaction, carbon monoxide plus 2 H2s yields CH3OH. Your before values for carbon monoxide and hydrogen go in. And you start with 0 moles of product. Now for the change row. Again, we don't have a picture, so we don't know which one the limiting reactant is. So we're going to test the first reactant. So if carbon monoxide was limiting, we would subtract all 0.5355, and that value gets carried over to the next column. And you would multiply by a fraction, and we'll repeat for the product. We copy the limiting value over, but products, remember, get that plus sign. Now for the coefficients, and you can think of that change row as coefficients, coefficient CC. The coefficient of hydrogen is 2, so the numerator is 2, and the bottom number is always the coefficient of the limiting reactant. Here, our coefficient of carbon monoxide is not written, but we understand it to be a 1, so that 1 goes down here on the bottom. And we're going to stop and calculate this real quickly because we don't know if carbon monoxide is limiting. We're doing a test here. Let's see if we have enough hydrogen. So we're going to punch in 0.5355 times 2 and I get 1.071. And you pause. Do you have enough hydrogen to continue? We will use 1.071 moles of hydrogen, and we have 2.5248. Yes, we have enough. So since we have enough hydrogen, carbon monoxide is that limiting reactant. Yes. So we're going to continue with our BCA table. Now for the product, its coefficient is 1. And again, the coefficient of your limiting CO is 1. Okay. And this is going to be 0.5355. So for your after row, you're going to take the before and combine it with the change. So carbon monoxide ends up being 0 at the end, and that's what we expect. It should be 0 because we said it was our limiting reactant. The hydrogen is going to be 2.5248 minus 1.07. So 2.5248 minus 1.071. 1.4538 moles left over, and this one 0. You don't have to show this, but I'm doing this for emphasis. We are making 0.5355 moles of CH3. Since you have extra hydrogen, hydrogen is your excess reactant, and our BCA table tells us we have 1.453 moles left over. And again, for emphasis, we are going to highlight our limiting reactant column. And notice that, first of all, the coefficient of the limiting reactant of 1 was carried over as the denominator in the fractions. And 2, the value that we subtracted from the carbon monoxide, our limiting reactant, gets transferred to all the other change columns. Okay, so to answer the rest of these questions, part 1, what is a limiting reactant? We already said carbon monoxide is limiting. So part 1, your limiting reactant equals carbon monoxide. 2, how many grams of product are formed? We'll go to your products. At the very end, we have made 0.5355 moles of CH3OH. The problem doesn't want us to solve for moles, but yet it wants us to solve for grams. Well, I know how to convert moles into grams using molar mass. We're going to take this, and real quickly we'll calculate the molar mass of methanol. You have carbon plus 3 hydrogens plus oxygen and another hydrogen. A molar mass of 32.05. Moles cancel, you're left with grams of CH3OH. So I take that value in my calculator and multiply it by 0.5355. And I get 17.16. And if we're rounding for significant figures, your given values in the problem, 15 grams, 5.1 grams, that's 2 sig figs. You go with the fewest number of sig figs, both are 2. So my final answer here has to contain 2 significant figures. So 1, 2, 17 grams of methanol carrying 2 sig figs. That would be your final answer for part 2. Part 3, how many grams of excess reactant are left over unreacted? So you go to your excess reactant column. For us, this is hydrogen. Hydrogen is in excess of 1.4538 moles. That means 1.4538 moles of hydrogen did not react. So part 3 here. 1.4538 moles of hydrogen did not react. That's how much extra we have. And we're going to convert this into grams using its molar mass. So 1.4538 times 2.02. I get 2.9366 in the calculator. And we're going to round this again for two significant figures. 2.9 grams of hydrogen remain in excess, and that is rounded to 2 sig figs.